Hey, thanks so much. It's a real honor to be here, you guys. Yeah, I hope to tie together a little bit of what I'm thinking about in machine learning to what I think we traditionally research in quantum physics. And, you know, what better audience than everyone who's changing the world with machine learning? I think Toronto's the center of the universe for this stuff. And, you know, hopefully we can find how we, you know, Toronto and Waterloo kind of can be partners in some of this exciting machine learning for quantum physics. So if you're like me and you Google things like quantum machine learning, you'll instantly get confused about what's going on in the field. And I think part of what I want to do here today is maybe just clarify a little bit about some of the recent advances in what we're calling quantum machine learning, or machine learning applied to quantum physics, and vice versa. And so there's two ways that our community of physicists talks about quantum machine learning. And the first is what's going to be the majority of my talk, which I think will hopefully be accessible to all of you guys. And that's repurposing, you know, machine learning algorithms or strategies for use in solving very difficult quantum problems. And I'll explain why we have to do this and so on. You can almost imagine, you know, right off the bat, you know, the idea that machine learning has to be involved somehow in the progress of quantum technology. You know, it's already an integral part of you know, semiconductor technology and chip manufacturing. You know, Intel uses machine learning to classify defects in their wafers and so on, basically facial recognition type software. So it's not a big stretch to think, you know, we could use machine learning and condensed matter physics to identify patterns of structure factors and maybe neutron scattering or STM images and so on. So I'll talk a bit about that and how physicists are already using machine learning for that. And from a mathematical standpoint, I think what's most interesting about this sort of early marriage of machine learning and quantum mechanics is implications for quantum, what we call Hamiltonian complexity. How well we can simulate quantum systems on classical computers. Okay, so that's kind of one of the themes that I'm going to talk about most of all. If I have time at the end, no, I'll have time. The last 10 or 15 minutes, I'll talk about the other aspect of quantum machine learning you might have heard of, which is using quantum hardware. And so quantum hardware, you might think of D-Wave, or you might think of maybe what IQC is doing at Waterloo. Okay, so some of this hardware is in maybe the far future. So we're going to start with you know, repurposing what's happening here, you know, in the machine learning community for use in quantum physics. And so just by way of introduction to my field, you don't need any knowledge of quantum mechanics, I think, to listen to this talk. If you're expecting to learn anything about quantum mechanics, sorry, I'll just apologize in advance. But what I mean by quantum physics is something that's very complex. We usually think of the wave function. So when we study quantum mechanics, the, say, electron, the thing we're interested in, has quantum numbers. Charge is one. Spin's a less familiar one. The spin of an electron is a quantum number, just like maybe a momentum can be, or a position. So you have all of these features of an electron, and it's described by something we call a wave function, which is some kind of imperfect mathematical description of reality. The wave function is governed, its time evolution is governed by what we call the Schrödinger equation. Again, you don't have to worry too much about that. But, you know, since the 1920s, we've known how to solve the Schrödinger equation for an electron in most cases of interest. And so what's different now, you know, what the challenge is now is not solving kind of the single electron or the single quantum number or the single particle Schrödinger equation. It's when you combine 10 to the 23 of these things together in either a material or a device or something like that, and try to predict what's happening at the macroscopic scale. And that's what my field, condensed matter physics, or quantum many-body physics, currently does. And some of the big problems we're working on are things like high-temperature superconductivity, okay, which is something we want to design. We want to design a room-temperature superconductor. This has been something we've been trying to do for 30 years since the experimental discovery of some of these materials. And so far, we've been unsuccessful. I mean, it's a very challenging problem, which I'll explain in the next slide. Another thing that we're trying to do in my field is design qubits for future quantum computers that are fault tolerant, that are stable. They're stable against decoherence from temperature, which is difficult to do. It's difficult to isolate something from its environment, like an electron, so that you can manipulate the quantum degrees of freedom. So we would like to design, kind of macroscopic qubits that have a topological feature that's topologically protected from decoherence. So that's another thing that we're trying to do in this field of physics. It's one of the goals. And again, yeah. Am I getting myself in trouble? Maybe incomplete, yeah. I don't know, perfect, yeah.
Consensus on that?
I don't want to define the word perfect. Yeah, I'm just trying to give a flavor for the fact that we don't know everything about it. Let me put it that way, okay? And the reason we don't know everything about it is it's what I'm calling infinitely complex. Now I realize maybe many of you are mathematicians, and I'm going to get myself in trouble with abusing the word infinite too here. So, physics, we think of infinitely small, the electron or the quarks, and infinitely large, like cosmology, And my field claims to deal with the infinitely complex. Again, to abuse this word. What does that mean? It means the size of the Hilbert space for this, 10 to the 23, this chunk of material is somehow bigger than the universe. The number is bigger than the number of all particles in the known universe or something like that. So again, it's an abuse of notation. So what does that mean? So I'll talk about why interactions are important, but in these difficult problems, one has to consider all the particles and how all particles interact. You can't just think of the single electron in isolation. And what happens is, even in a classical case, so imagine I have electrons on a two-dimensional lattice. The charges are confined to the lattice site, like this happens in a real crystal. And only the spin degrees of freedom, I'm just going to imagine there's two of them for now, spin up, spin down. Those are the only degrees of freedom at the energy scale we're interested in, say. Even that state space, or Hilbert space, the state space is 2 for the two states locally to the n, where n is the number of electrons. And like when n is 200 or 300, that's like 10 to the 80 or something like that, right? So this is what I mean by infinitely complex. The fact is that if you have a mathematical equation that governs all the interactions of those electron spins, like a Hamiltonian, just a scalar quantity that says, I'm going to use this Hamiltonian quite a bit in this talk, the Ising model. I have SZ components, or SZ components, if you're in Canada, of the spins of the electrons. They might interact, and this means all nearest neighbor pairs with a Hamiltonian like this is very common. If I wanted to calculate something like the energy of that macroscopic system, I have to perform a trace over all those 2 to the n configurations, which is mathematically complex. It's exponential. It's too difficult to do. Yep.
You guys take this implementing. How many qubits would that thing need to have for you to be useful in your fields?
Yeah, so I'll talk a lot about D-Wave maybe at the last part. So yeah, that actually depends what you want to do. Yeah, it depends integrally on what kind of calculation you want to perform on the quantum computer. So remind me near the end if I haven't answered that, but I will get to, hopefully I'll get to that, yeah. So it's actually confusing. There's many reasons why you might need a quantum computer to battle this complexity. And so that's one thing that I hope to clarify or maybe confuse you more about during this talk. But just already you see that classically, because this is just scalar quantities, this can be a very difficult calculation. Quantum mechanically, a Hamiltonian that has, say, degrees of freedom, the SZ components of the spins, plus what we maybe call a transverse field. So if the electrons are, truly quantum mechanical, if you put a field transverse to the Z direction, it's quantum mechanical in the sense that, those two operators don't commute. So now the Hamiltonian is no longer scalar, it's some operator. It's some operator quantity. If you want to calculate the energies or specific heats or susceptibilities, you have to first perform the diagonalization of that Hamiltonian. So you're diagonalizing something that's 2n by 2 to the n. And so you see there, that's a very complex mathematical problem. And actually, in practical terms, in condensed matter, for electrons and spins and bosons and things that we're interested in calculating this exact diagonalization for, we're stuck on like maybe a dozen or 20 or 40 quantum particles. So when you hear quantum supremacy, a computer that could beat the best classical calculations, it doesn't have to be very big. So in some way answering that question, it doesn't have to be very big to be quantum supreme for the current diagonalization routines we have. But like, hopefully, you're saying, well, we already know how quantum mechanics works at the single particle level, and we've already harnessed it enough to design your iPhone, right? I mean, the the silicon chip in your Intel designs these things essentially from the atom up, right? And atoms are quantum mechanical. So how do we reconcile this view with the fact that all of our modern technology relies on understanding quantum mechanics? And there's a very important reason, and that's that essentially that single particle Schrodinger equation's enough to understand most of what I call maybe conventional or current technology, especially conventional computers. And Walter Kohn, and this is a Kohn-Sham equation for the local density as a sum of single electron wave functions, made huge contributions to this. Nobel Prizes were given out. And what we do in semiconductor physics, which we used to call solid state physics, is take advantage of these single electron approximations. Okay? And that's enough to describe metals, semiconductors, all sorts of things. It's not enough to describe those interacting quantum systems like that topological qubit or that superconductor that I had shown on the previous slide. There's other ways to battle complexity for interacting systems that maybe you're familiar with. One is stochastic, just generally doing sort of Markov chain sampling of that sum. So instead of doing the full 2 to the n, you sample just the important parts of Hilbert space or state space. So I'd call that Markov chain Monte Carlo. Basically, you just run a Monte Carlo through this higher dimensional space and calculate any observable as an average of the energy, say, that you measure for each one of those configurations. And you can do this in quantum mechanics. All you have to do is think about a d+1 dimensional like Feynman path for your configuration, but we do this all the time. This is actually what I specialize in, is sort of quantum Monte Carlo, stochastically solving quantum many-body problems. One thing I want to talk about in a little more detail is the idea that we can compress the quantum state, the many-body quantum state, or we could decimate the Hilbert space. So we have this 2 to the n, but maybe only part of this, say, spectrum is important. And much modern research in my field goes into looking at the physically relevant corners of that state space and sort of, I guess, decimating or truncating the Hilbert space so that we can only deal with something that's computationally efficient, by which I mean polynomial in the system size. Okay? And so when you start seeing stuff like this, you start wondering, can machine learning offer some kind of new strategy for us to battle this complexity? To take what on the surface seems like an exponential problem, but extract maybe just the features that are important enough for us with some polynomial type algorithm. Okay, so that's kind of what interests me. And I'm just going to focus on to start supervised learning as sort of a strategy to do this, which I think will hopefully get us all on the same page in terms of features and complexity and so on. So, any questions about my my introduction before I go on to supervised learning? Good. How many physicists are in the audience? Good. Well, I'm relying on you guys to save me from any bumbling mistakes up here. So. Supervised learning. Do we know what it is? We're not so different, you and I. We maybe want to classify pictures of cats versus dogs. I'm talking about classifying phases of matter through some, we can imagine producing snapshots, some sort of representation of maybe the state of the electronic spins. This is the error correcting regime of some topological qubit or even some topological features that are difficult to maybe see. And so, if I can assign labels to these features that I'm interested in, in the physics context, then I can perform supervised learning. So I'm going to go back to this idea of the Ising model, and because it's like our hydrogen atom. It's our simplest many-body system that we study that has interesting properties, and we're going to perform supervised learning on this. We're going to imagine just the Z components of the electronic spin, so it's essentially classical. But we're going to impose a Hamiltonian. And what this Hamiltonian does is every nearest neighbor, it wants to, because this is the Boltzmann probability, this is the probability for thermally realizing that state given an inverse temperature beta, so 1 over T. We can see just by maybe drawing a couple spins, looking at their interactions, that at essentially 0 temperature, we'll have a fully ordered state that's called a ferromagnet. All spins or all degrees of freedom point in the same direction. If you go to the infinite temperature regime, then nobody cares what the neighbor is doing of any given spin. And so you get a completely random up-down pattern that we call a paramagnet. So here's a ferromagnet in 1D. I can imagine mapping spin up to black, and I would get maybe if I was in 2 dimensions, I get something that looks like one of these images, maybe some defects. The white spins are spins pointing down. And then at infinite temperature, I can imagine a mix of up and downs completely randomly in the paramagnetic state. So from our knowledge of these 2 states, let's draw an analogy to supervised learning for handwritten digit recognition, like what you would do with MNIST. So in my case, I have data. I'm going to do a 2-dimensional, I'm going to have a black box which produces 2-dimensional images, which are basically roughly the same size as your MNIST data set, which I forget off the top of my head. It's 20 by 20 roughly or something like that, 28 by 28. And I want to assign labels to things. Now, different images can have the same label here. I can have all spins up at 0 temperature or all spins down. So I want to label both black and white images as ferromagnetic, and then completely random images as paramagnetic. Okay, so the idea is to perform some sort of supervised learning, but take the same strategy or the same structure as I would use for MNIST, but just replace it with a simpler labeling system. Okay, does that make sense? Does everyone know what this is? Question?
Different types of ferromagnets?
Just those 2, all up, all down.
Because I don't see how these problems are that similar, because the hard particle is labeling numbers is that they have shape. Where's the...
Right, yeah. So I'll talk, so there's other types of ordered patterns, right? But I'm just starting with the simplest. I mean, this is too simple, right? But I'm going to tell you why I'm doing something very simple, and then we'll build up. Yeah, so you know what's difficult here. I mean, this is overkill. But what I'm doing is transferring your technology, and I'm going to apply it to my simplest, many-body system, and we're going to understand why it works, basically. Does everyone recognize the feed-forward neural network? Am I way off base here? Okay, I'm like, if I show this to the physicists, they're like, whoa, back up. Like, okay, so all I'm doing is I'm taking the simplest possible thing. This is what I've been giving my students, for example, to start on the problem. We're very familiar with the Ising model. We know how to produce configurations, say 2-dimensional configurations. So let's just feed those into the input layer. And again, the dimensionality is lost in some sense. I mean, we're working in a 2-dimensional system, but we're just going to strip out all the pixels, black or white, in some sort of pattern, and feed those in some arbitrary order into the input layer. The output layer is only going to be ferromagnet and paramagnet. And so, like this black, this is our speciality in some senses. We produce these types of images, if you will. That's what quantum many-body, physics, computational quantum many-body physics does, is study this type of thing. So it's like we own a whole bunch of data. It's on it's on SharkNet. We have all sorts of images. And now we're just going to classify them with what you guys build. So L by L input layer. I'm going to start with 100 units and sigmoids. Okay? So just very simple. And so just let me point out, in the Ising model, I don't have to stay at 0 temperature and infinite temperature. There's a whole range of temperatures, right, which produce sort of the same, ferromagnet, but you get more and more thermal defects in it. So it's a little more complicated than just trying to classify something that's all black or all white, right? I want black with some thermal defects. And the higher my temperature, the more thermal defects happen until my ferromagnetic phase abruptly transitions over a phase transition into the paramagnet, the complete random phase, okay? So this is a feature of the two-dimensional Ising model. This is what I would call a phase diagram. There's a well-studied and highly non-trivial in some sense critical point, or phase transition, separating those two phases. So what I'm going to do is I'm going to train that feed-forward neural network on a range of temperatures. I'm hoping it's general enough that at any temperature below the phase transition, it can identify the paramagnet, no matter how many defects are actually thermal defects are present. So, question? In the thermodynamic limit, yes. So when n goes to infinity, it's an abrupt change. It's a phase transition.
It's one side ferromagnetic and the other side paramagnetic. Magnetic fields.
There's no magnetic field. No, it's spontaneous. So the Hamiltonian is spontaneous symmetry breaking. Yeah, no, it's difficult. Yeah, okay. I'll just say there's a spontaneous change in the magnetization. So it's like if you have a magnet that sticks to your fridge. If you heat it up with a blowtorch at some point, it won't stick to your fridge anymore. There's a spontaneous change if you randomize it enough. So that's what. Okay, that was probably, I embarrassed myself in front of the physicist, but that's. I wasn't prepared for that question. So there's an abrupt change. There's a physical reason, and spontaneously you can pick white or black at zero temperature. It's a spontaneous symmetry breaking. So I'm just going to train at 5 temperatures above, 5 temperatures below that abrupt change. Okay, 10,000 images I think we did. I'm going to talk about the cost functions more, because really the cost functions are what define the optimization landscape, right? You have this like funnel, or this I would call it a free energy landscape, but you're trying to find the minimum of some optimization landscape defined by, in this case, we use some cross entropy. Okay, you guys probably recognize this. So we train this thing, and then we test it on new images that I've produced, from my supercomputers. Okay, this is the result of the output neurons. Remember, there's 2 of them. After training on the test set of tens of thousands of different images, varying distances from the phase transition. So, I love this 2-slide setup all of a sudden. So remember, this is 2.269. So this is the thermodynamic phase transition. Blue is my cold or my low temperature output neuron, and this is my high temperature. And so you can see that red goes from 0 to 1 and vice versa, with increasing, I guess you would call it accuracy, as you increase the system size towards what we know theoretically is the thermodynamic phase transition. So it generalizes enough that if you train it at a fixed range of temperatures, the defects that are thermally being populated don't screw up your classifier. And for the physicist, which is, what's actually really fascinating about this, is if you do a proper finite size scaling analysis. All right, I'll take your question first. The L by L? Yeah, L by L. I had it on, we needed on the third last, Yeah, so it's square root of the number of pixels. Yeah. Okay, so what's really cool about these output neurons is if you do a proper finite size scaling analysis, like maybe look at, this is different than what we would do with Monte Carlo. This is not an estimator for me. I'm just looking at the output of the neural network. But if I say, look at where the curves cross 50%, and I plot that as a function of 1 over the system size, I do some rough extrapolation, I see that I get the proper thermodynamic transition, within the errors inside all of this. So I'm doing a proper sort of physical analysis on the phase transition when I train this thing, in a very sort of simple way. Exactly what I would do with MNIST. Even better, for the few of you who can appreciate this, I can extract the critical exponents by doing a finite size scaling collapse of the output of the neurons, of the output neurons, just from the scaling theory from the RG. So if you don't know what that means, that's okay. But you can actually extract universal numbers for that phase transition straight from the feed-forward neural network. So it tells you something's going on. It's somehow representing, the phases and even the phase transition in a very powerful way. Something that's very useful for us and very non-trivial. So. And why I like the 2D Ising model, this is back to your question, is we don't need to crack open the hidden units and try to see what the features are, because we know somehow it should be learning that magnetization. Either it's 0 or it's finite. And we can construct a toy model, for the feed-forward neural network with only 3 hidden units. And I won't go into this. You can look at the paper here. But this model of hidden, 3 hidden neurons, which has weights. So this is n by 3, biases. And now I basically can understand that my argument of my activation function is related to the magnetization, which I'm calling M. All magnetization up, all magnetization down. This is up or 0. So for some reason, that's the features that you can construct analytically, which will give you exactly the same curves here. So you don't need 100 hidden units. In this very simple case of the Ising model, you can extract all this physics with just 3 hidden units. So I think that answers in some sense, I think, why we do these simple models, is because we can boil them down to something that we can understand with 100% analytical accuracy, if you will. Any questions on this? What's actually interesting is generalizing this to problems that are of immediate interest to the physics community. So a simple thing you can do is test maybe either your toy model or your pre-trained neural network on other lattices with different phase transition temperatures. Maybe it's like transfer learning, you might call that. I don't know. And indeed, you can extract physics at other. Once you understand that your features are the magnetization, it makes sense. You can extract phase transitions where that magnetization is the order parameter. But if you have other ordering parameters, ordering patterns in more complicated systems, you can train these feed-forward neural networks to classify things. So I won't get into that, but this seems more realistic. You might have some neutron scattering pattern in Q space, and you want to classify whether or not that's some sort of order, right? Okay, so that's all. I'm just advertising that works. But I want to get into more interesting stuff. So what's more interesting is from a physics perspective, is models without clear-cut order like magnetization. So I'm going to show you 2 examples. Maybe don't worry too much about what the Hamiltonian is in these models, but I have one that's sort of a model for emergent electrodynamics. It's called square ice. What it is a Hamiltonian where you have a vertex, the degrees of freedom are on the bonds, and at low temperatures, you're allowed to have only 6 possible vertices. So the ground state is every vertex has to be constrained to be one of these 6, but there's no other rule. And so it looks disordered. There's no magnetization or any clear ordering pattern. The question is, can the feed-forward neural network learn to recognize this ground state? And I'm going to train at 2 different temperatures, if you will. One where this constraint is obeyed, and one where every spin's completely random. So let me just show you what those look like. All right, good. Let's see. Can I go back and forth? No. Okay, so one of these is completely random, and one of these has the constraints on every plaquette. And you can ask your eye if you can pick those out. And I forget which is which now. But based on the order here, I think this is the completely random one. So every one of these is assigned white or black with a probability 1/2. Here, if you know where the plaquettes are, then each one of these should have one of those 6 patterns. If I take my same feed-forward neural network with 100 hidden units, and I do 10,000 or whatever, 20,000 training set at these 2 types of patterns, it basically learns to distinguish them with basically 100% accuracy. So it's maybe hard for your eye to see the difference right off the bat, but no problem for the neural network. Okay, so this is important. We can use a feed-forward neural network to classify emergent theories of electrodynamics. I mean, in some, that's what it's telling us. That's physically interesting. I can do another one here. This one's more important for designing a qubit. Same sort of idea. Here's the Hamiltonian. The degrees of freedom are on, again, the bonds, but this one emits 8 different plaquettes in the ground state. Okay? So it's 0 temperature. Your lattice is made up of these 8 different patterns. And at, say, infinite temperature, everything's just random, 50-50. This is the simplest model for a topological qubit. This is what Google's trying to build in Santa Barbara. John Martinez is working on this surface code. It's essentially the quantum version of this Hamiltonian. This thing emits some sort of topological order that's robust against decoherence. So it's very important that we understand sort of this type of, I guess if you will, topological order and the features and so on. One of these images is the same. This is probably it. It's the infinite temperature. Everyone's 50-50, okay? Just randomly 50-50. You can actually see that this one's different. There's all sorts of clusters. This is the topological phase. This would be my, topologically protected qubit in principle. Each one of these things would be maybe an electron spin. And if I arrange these things in this order, there'd be like a flux, if this is a torus, there'd be a flux through this qubit that could be either up or down, and that would be my, what they call logical qubit. So this is one of the main designs that people are working on for quantum computing, for gate models. But the feed-forward neural network, the simple one I have, just does not classify this thing. And I do not know why. So if someone here can answer that question, maybe you'll build a quantum computer. I get 50% accuracy. There's nothing I can do to train that simple feed-forward neural network to distinguish those two phases. And so, I don't know what to say. There's something about that phase, about either the exponential decay of correlations or something that makes it very difficult to classify. It's very interesting. Just for this crowd, I might not always say this, but if we do a convolution neural network, which you are all familiar with, hopefully, then we can classify no problem. So we built a simple one with 2x2 filters, fully connected, rectified linear units, softmax output. That works. That classifies 100% accuracy. And what I think is going on is, which is what maybe these convolutional neural networks do, is what you're doing is putting back in some information about the dimensionality and the locality, because the filters tell you about the locality, which pixels are next to each other, right? And that's somehow important in these topological phases. You've got to learn this constraint, maybe, is one way of thinking about it.
Are you familiar with Mitzi's original work on the spectrum?
Nope.
What you can do is basically you can utilize the keyboard neural network just as hyperplane.
Oh, yeah. Okay. I see. So, yeah, we haven't looked at this much more, but this would be interesting to see, I guess, what the features are. My big question is detect the local constraints, but we also know there's some topological features in these objects. So I think what we're interested in the long run is detecting topological. Maybe you guys know if you can detect things like hop flinks and stuff like that. I think that's very interesting for physicists also. So again, you probably realize it by now, but I'm a complete amateur in terms of machine learning. So I've only been doing this for a year or two. So I welcome any any suggestions or comments, and also please excuse my poor citation for your field. There's no excuse, but I want to move on. Supervised to unsupervised. Okay. That was this classification problem. Why would I want to do unsupervised learning? Well, one thing that we've done is now taken this, taken a neural network, which I'll explain, which you're familiar with, which can generate images of that topological phase. So a generative model. And in that model, I can also have it generate, say, thermal defects for the single electrons. I can thermally, we always show a lightning bolt. There's a lightning bolt, some external influence that might flip an electron spin with some probability, for example. And it's a big problem in quantum, designing quantum computers. How tolerant is that topological bit to the probability of single electron defects? And so we did this using a generative model, which I'll explain. We basically generated these patterns with different probability for thermal defects And we can calculate the probability that the whole topological bit's going to fail. So I've wrapped this into a torus, and I can calculate the probability that that arrow is going to disappear. It's either up or down. It's kind of the bit states. And if you put enough errors in there, it loses all meaning. It's called the threshold. So we can use generative modeling to calculate the error correction threshold for topological qubits. So that's just a motivation. I think that's really cool. And that's that's an application, essentially, of machine learning, in quantum computing. So what is this? I can go through this pretty quick, I hope. Generative model. I have a target distribution. So this might be my Hamiltonian that I kind of glossed over. These things that give you the constrained vertices, for example. I have a partition function, and I have an inverse temperature for a thermal defect. There could be some other mechanism for defects. I hope you guys recognize this, right? So we use a restricted Boltzmann machine. And the goal is, in generative modeling, now we don't have labels, right? We basically want to do some sampling on this thing once trained so that I can produce this image, or produce the distribution, sample from that distribution to produce samples that correspond to these images, say. Okay? How is everybody on the RBMs? Yeah? I'm in the right crowd again? Hopefully, okay. I love this. It's so much easier for me not to have to understand what's going on here. No, just kidding. So one thing I want to say about the RBMs is, they're energetic models, again, in some sense. You have an energy, weights, biases. We're just doing something simple. But the marginalized, is that what you call it? The probability distribution on the visible units, where you perform the marginalization or the trace over the hidden units, that's the thing that's supposed to model that physical target distribution, right? And if you took any quantum mechanics, somehow you can imagine that probability is, or that maybe the probability density is related to the wave function. Okay, so maybe in some sense there's a Hamiltonian. If you take that trace, I think you might call it the free energy. I might call that the energy, or the Hamiltonian. So somehow you're doing what we call an inverse problem. You're feeding this thing a training set, and you're calculating I think what you call a free energy, or what I might call a Hamiltonian for the problem. Then you're performing Bloch-Gibbs sampling, which produces, configurations according to the proper probability distribution, which is what I would call the wave function, or the wave function squared. So it's not such a far stretch to say what this is doing is producing a model of the wave function, or it's representing a wave function in some way. Okay, and that gets back to this Hamiltonian complexity issue, which is currently what's very interesting for physicists. Is an RBM an efficient representation of the wave function? And I think the definition of that is whether or not for a given system size, quantum mechanical, classical, whatever, L by L, whether or not I can represent the wave function, which means reproduce some physical observables with a polynomial number of hidden units. Okay? So the number of hidden units doesn't have to grow exponentially as I grow n. That's a very interesting and fundamental problem in sort of quantum complexity theory and Hamiltonian complexity. No, it's very relevant. So so I think I'd say there's two efficiency issues. One is representation, and one is maybe training. And physicists have got into this problem before. We found efficient representations, but we haven't been able to train them or maybe calculate things on them efficiently. You're right. Oh, I see. Right. I would call that the ergodicity time, maybe. Yeah. So that can be a problem. So the one thing I like about the Bloch-Gibbs sampling is it seems to not have a lot of ergodicity issues compared to conventional quantum Monte Carlo, but maybe that's debatable. I'm not sure. So that's a really good question. I haven't thought about that at all. But we definitely have these ergodicity issues, time to reach equilibrium, or I would say time to maybe sample all of phase space. If that's exponential, what I would say is that then we have non-ergodicity. So I'm not really talking about that, but it's definitely an issue. Yeah. Training, I think training too. The question about whether you can train efficiently is maybe a third issue then. So let's just think about representation. I think you have to have good representation, and then you got to worry about whether or not it's practical, right? Okay, so training, I mean, maybe I'll just skip this. We train Ising models. We can calculate distributions exactly. We do KL divergence, contrastive divergence, K, small Ks. These things tend to train fairly well in the classical case. And here is what some output of this generative modeling, this RBM, looks like to me. So what I've done here, okay, so I've trained on configurations produced in some black box where I know the Hamiltonian. Same thing, you know, same type of images. Once the RBM's trained, I do block-Gibbs sampling, and I'm looking at the visible layer, and when I get a configuration, it's like I'm doing that sort of Markov chain, right? I'm calculating this in the same way I would with a conventional Monte Carlo, Markov chain Monte Carlo, where my estimator for the parameter set, you know, it's just 1 over the number of block-Gibbs samples times the observable in that, you know, so it's sampled according to that target distribution. So here's an interesting estimator. It's a specific heat. It's a derivative of the energy with respect to temperature. It's very fundamental. You can measure this in an experimental magnet, you know, in a bulk measurement in the labs in the physics department. So the black is the exact answer for a given L by L. I forget what size. 16 by 16. And you can see as you're near 0 or infinite temperature, the ferromagnet or the paramagnet, you get perfect correspondence of this estimator with a small number of hidden units, 4, 16, 64. They all basically give you the correct estimator. What happens near the phase transition, remember this special point where you get this abrupt change between paramagnet and ferromagnet, is if you don't have enough hidden units, you're not getting the right answer. So it seems, it maybe makes intuitive sense. This is not a complete or accurate representation, I would say, of the wave function. It doesn't see the right Hamiltonian to reproduce the observables. So that's very important for us in physics because, physics has studied these phase transitions for a long time, and there's a very clear theory for, the physics at the phase transition, and it's called the renormalization group. Ken Wilson, Fisher, others in the 70s learned how to describe the important points, the important features of a phase transition using a type of coarse graining, where you take your microscopic model and then you perform some sort of coarse graining to a different model with couplings J prime, J double prime, and so on. That process, which is called the renormalization group, leads to what we call fixed points, which are described by very simple field theories. So I know I'm probably not talking to anybody specifically in this audience, but I just want to get the point across that there's a Nobel Prize was awarded for, or maybe more, awarded for the renormalization group, which tells us a very compact representation of features at phase transitions. And people have speculated that, near a phase transition here, you might need a deep Boltzmann machine or some sort of deep neural network in order to get faithful representation. For the same reason you need the renormalization group to extract features near that phase transition. And there's actually been a lot of work in exact mappings between deep learning and the RG. So I think this is a really non-trivial and interesting direction that physicists and machine learners can take to try to maybe crack some new problems and understand things. Yes. Yeah, that's what I would call it, right? And at some point in the RG, you're infinite in the visible layer, and you keep going forever. But I think in practice, it can be a finite-sized machine. Yeah. So we're actually currently studying this. If I do a deep machine, can I improve this? Maybe with the same number of parameters. If I had the same number of total parameters, do I get a more efficient or a more powerful representation with a deep Boltzmann machine versus a shallow machine? That's something very concrete that we could look at here. Getting low on time, so let me skip to quantum computers. Okay, this representation issue is important. That's all I want. How much time? When did we start, by the way? 10 minutes? Let's slow down. So efficient representation of the wave function in the quantum case is very important. Okay, we have, when I have a quantum mechanical transverse field, it's in some sense complex in a way that's maybe similar to that phase transition case, but a little different. But people in my field, and people at Perimeter, and Principal Guiffre, Vidal, and others, work on efficient compression algorithms. So how can I take that quantum Hamiltonian, or the wave function that it produces, say, and have an efficient representation? So there's ways of reducing the exponential complexity to polynomial by taking a wave function's coefficients and writing it as what's called a matrix product state. I mean, there's a bond dimension for the matrices there. I was going to talk about this, but what I did instead is I put a reference to a blog post by my friend Miles Studemeyer that explains tensor networks in physics in the language, I hope, of some machine learning. So if you're interested in this type of representation, just follow this link here, and there's kind of a nice explanation. But the point is, in physics, we've found physical reasons, low dimension, low entanglement, physical reasons that give us efficient representation. Okay, and there's increasing evidence now that neural networks like these Boltzmann machines provide an alternative, maybe perspective on how you get efficient representation in the quantum case. And actually, if you look, these are on the archive in January. So there's 3 big papers on the equivalence of restricted Boltzmann machines in tensor network states. So now the question is, what is a restricted Boltzmann machine in, kind of capturing that we can relate back to the physics that we understand from these conventional compression schemes in physics, right? Efficient representation in quantum many-body states with a deep neural networks. So this is kind of a mathematical study of this representation issue. This is where modern, what I would call quantum machine learning, is going to make the most progress in the next year, say, is in these types of issues, relating deep machines to quantum wave functions and representation of quantum wave functions on classical computers, just to predict the future. This leads into the quantum computer. I can make a generative model for this, what is this representation? I can take this model and sample it, images of this quantum model in the same basis as I've been working in, which I call sigma z. So I can get the same types of images restricted to the z basis, but they're produced by the quantum distribution. And then I can train a classical RBM, and I can exactly, through quantum Monte Carlo, look at features like correlation functions and find that I get the same, I can reproduce these features. This is something we've been working on. What's really interesting is you can make the weights complex in the RBM. And you want to do this sometimes because the wave function in quantum mechanics has to be complex in some cases. I mean, there's a phase, there's, a magnitude and a phase for the wave function. So in order to capture that wave function's sort of amplitude and phase, you can train a RBM with complex weights. And what my friend Giuseppe and Matthias Troyer did, Troyer's at Microsoft now in Seattle, is did reinforcement learning on an RBM. So forget that training set. Just look at the visible layer, the energy, minimize the energy. It's like a variational quantum Monte Carlo with a RBM as the variational ansatz. It's really cool. They've gotten energies, as you increase the number of hidden units, that have beaten PEPs, which is one of these tensor network things. So they've beaten some record for variational energies, and that's why this is in Science. This is a really interesting paper I would recommend to anyone who's interested in quantum versions of this. This leads into why use a classical computer, right? Why not just do all this on quantum hardware? Then the representation issue in some sense is trivial because it's polynomial in n by construction. Every qubit is that quantum transverse field Ising model Hamiltonian. And so that's the kind of the point of quantum hardware is the classical computer, it doesn't have to represent the Hilbert space with classical information. It represents it physically. Be aware, when people say quantum computer, there's several things that people talk about. Number one is the annealer. This is what D-Wave is. The quantum annealer, I'll talk about this, is a specialized piece of hardware specifically designed to solve optimization problems. Okay? So this is the rough optimization landscape that I showed before. So these are very easy to build. Not very, that was wrong. These are the easiest to build. They're difficult to build, but you can arrange noisy, messy qubits and still get annealing out of it. I'm going to explain that. An analog quantum computer, which I'm not going to talk about, is more like an emulator. They're often done with cold atoms trapped in lasers. So you cool these things down to 0 temperature. And the atoms emulate, it's like the electron. Remember I said the electron is spin degrees of freedom? You literally put the electrons in a highly controlled environment with no external noise. And so it's an emulator. It's like an analog computer in the sense that you're building the quantum system that I was trying to simulate on the classical computer. And then what most people think about when we talk about quantum computers is the universal gate model. This is the digital quantum computer that's kind of the analog, it's the equivalent to, your iPhone. It has gate operations, which you can encode digital logic and solve various problems. And this is extremely difficult to build. This is something that's in the far future, okay? So let me just talk about the annealer first. I mean, I could give a whole talk on quantum computing, but I just want to give you kind of the flavor of how machine learning fits into quantum computing here. So when people talk about quantum machine learning, they most often talk about the annealer. So the annealer is, a way of defining this optimization landscape and also finding the global minimum, if you will. And intuitively it's done through tunneling. So annealing usually means you might have some temperature, so you have some thermal excitations, which let you hop over these peaks, and you slowly cool down. And so hopefully you're hopping around here, and you slowly cool down, and as you cool down, you just fall into that potential minimum. Okay? What the quantum annealer says is, well, you can also tunnel. In quantum mechanics, electrons can tunnel through barriers. It's the same idea. You can just tunnel right through these mountains, which in principle makes sense. Sounds like you can get speed ups and annealing times and so on, but as a caveat, there's no mathematical proof that there's any quantum speed ups for annealers. Okay, so even though they're easier to build in some sense, it's not clear that, unlike Shor's algorithm or one of these factoring algorithms, there's no clear exponential speed up for these annealers. So the optimization problem is defined through the Ising coefficients. This is all it is, that Ising model that I've been telling you about over and over. All you do is generalize the JIJs, the interactions between nearest neighbors. So now I have some sort of qubits. I've generalized the nearest, the interaction, and that defines the optimization problem that I want to solve. So you can take whatever your model is that you want to do machine learning on, and you can encode that model or that optimization problem into the Ising interactions. And if you can do that, and if you can map it to D-Wave's hardware, then in principle you can run this on D-Wave. So this is D-Wave's, this is this lattice, but it has this complicated hardware, this complicated interconnect. And people work on mapping interesting problems between here and there. D-Wave has a transverse field that they apply, which gives you the tunneling, but they also have other effects which are uncharacterized. We don't quite know how warm these qubits are, how much noise is kind of environmental noise is affecting them. But in principle, you can just go ahead and run the thing. And that's what D-Wave's great at. You can encode these optimization problems, and you can perform quantum annealing. So there's been theoretical and experimental work on quantum annealing. Some of these might be out of Google's quantum AI group down in California and so on. They have some of these machines where they're doing these types of problems. So the idea is you turn on a transverse field, maybe you shut off the optimization problem or make it small, and you slowly change the transverse field as you move through this annealing direction, and hopefully you fall again into that global minimum. That's like training, right? You've trained somehow your system to find that, solve that optimization problem in some sense. So that's what these papers are about. And in the end, the transverse field shut off. That's important. So the quantum mechanics, the output of D-Wave is this classical problem. It's the solution to the classical problem. And the quantum tunneling is just a way of getting through all those energy peaks, or those free energy peaks, or whatever you call it. You can also imagine keeping that transverse field as a parameter in your RBM. So you can make a Boltzmann machine that has a quantum transverse field as a parameter that you train. And that's a lot more difficult. It's actually, we've worked on that with collaborators at D-Wave. And there's, it's in principle, it looks like you get very powerful representation. You can get KL divergences that are very low. These are simulations of quantum annealers. So you can get improvements on KL divergences for certain problems, but it's not clear how to train the quantum part of the machine. There's still a lot of theoretical work that has to go into these. This is what I would call a true quantum, Boltzmann machine, is with a quantum parameter that you train. Okay. So in principle, theorists are working on this, and D-Wave's been performing some kind of rudimentary experiments on this type of problem. That's what D-Wave's doing. Yep. Right.
I mean, that those qubits,
yep.
Because of the complex mapping, you have a percentage that goes away when you have to mapping the factors on the chip.
Right.
So with the amount of macrological qubits that you can work with, do you see the firm chip going to be useful for some of your classification problems?
You can definitely construct a classification problem that chip in principle would do quantum annealing on or make a quantum Boltzmann machine that you couldn't do with a classical simulation of the same architecture. Classical meaning I do it on a classical computer, I have to have some D+1 nonsense in there. But I'm not sure that I can say that problem is one of these problems I've been talking about. So it's not clear that it's one of these physically interesting problems for condensed matter science, say, okay? So you can definitely construct a problem that you can do that, but I don't know if it's a problem I'm interested in terms of, say, building a high-temperature superconductor or something like that. So that's yet to be seen, I think. But there are people who map maybe interesting mathematical problems, maybe some KSAT problems and stuff like that, to D-Wave hardware, or some graph or some networks that have some optimization landscape difficult to solve. So there may be more mathematical kind of problems that are interesting, but yeah. That was an unsatisfying answer, I'm sorry. Okay, so I can talk about that kind of stuff ad nauseum, but so let me just, one slide about the universal machine. The other time that you'll hear quantum machine learning is from the community of who work on algorithms for future quantum hardware. And I hope one of the things that that came across today was the idea that this is difficult to build. We're still trying to model, with classical computers, how to construct these qubits. And we're not even sure what the qubit's going to look like. Is it one of these topological ones that Google's building? Microsoft's now invested in a topological Majorana fermion-based kind of architecture, which is completely different than Google. So those are two big players. IBM has some sort of superconducting quantum circuit topological architecture they're working on. I showed a picture here. This is from the Google group, Martinez. Essentially the state of the art from last year. That's 9 physical qubits. These are like 9 digital electrons that they have to build enough of these things to wrap into a torus, and that would be the logical qubit. And people think you need like maybe 1,000. So you might need 1,000 of these individually highly controlled superconducting quantum qubits arranged on a circuit that, has this proper topological property to make a single qubit, which then can be used for something like Shor's algorithm for breaking RSA encryption. And I think for 2048-bit RSA encryption, the minimum amount of logical qubits you need is something like double the key, so it's like 4,000. So you need 4,000 times 1,000 minimum, never mind all the gates. So that's how far away we are from this type of quantum computer, okay? But once you get that quantum computer, people are working already, lots of people work on this, on the algorithms that we could put on those quantum computers. And so the other type of quantum machine learning you might have heard about, which I'm not even going to talk about, quantum PCA, I think there's some exponential speed up possibly for quantum PCA. These support vector machines. There's algorithms to put parts of these on. Lots of the algorithmic parts are related to Shor's algorithm, these factoring problems, Grover search, quantum phase estimation and Fourier transform. So the kind of building blocks of the digital algorithms that run in quantum information science, those can be transferred piece by piece to give improvements in things like PCA, okay? So that's possible, but again, that's, I don't know how many years in the future. So hopefully that kind of clears up what's meant in that, that aspect of quantum machine learning. And here's a very recent and interesting review article by Jacob Biamonte, Seth Lloyd, Nathan Weeby's at Microsoft, in Redmond. So this is a nice review of all of these quantum machine learning algorithms for future hardware. That's it. So I'm interested in cracking the complexity of quantum matter. We've been designing algorithms for decades. Is machine learning going to be better than the things we've designed? It possibly, I would guess, in some, very interesting cases, like in high temperature superconductivity, machine learning can make significant progress where we've been stalled for, 30 years or something like that. We need to do this. I argue that we need to crack these complex problems just to design a qubit, just to know how to design the error-correcting codes for, say, a topological qubit, which is the only kind of hardware fault-tolerant qubit. These are the same problems that we need to solve in order to solve high-temperature superconductivity. So you could say, well, I want to see floating trains. Floating trains and, I don't know, a quantum computer might be the same type of complexity to build. But what's great about machine learning is you might find specific instances of problems where the neural networks or the Boltzmann machines or something, maybe they don't give you kind of exponential speed up in complexity, but the prefactor could be much smaller, and it could enable us to solve some of these problems. And then once we solve those problems and we build, universal hardware, or even improve machines like D-Wave, these noisy annealers, then all sorts of new machine learning will open up, and we don't even maybe know all the algorithms possible for quantum computers yet. So, okay, thanks for your attention.
So this mapping, exact mapping from the deep Boltzmann machine to that specified, the deep Boltzmann machine was specified in units and weights, or is it something that can be learned from that?
So I think that in that specific paper, there's a mapping, like if you look at a local region of bits or pixels, and you do this map, this coarse graining, that's mapped from the RG specifically to something that would look like weights in a Boltzmann machine. So it's like the specific sort of steps of the RG have been mapped. And it was done in practice on a finite size machine. I forget how many, but with a decreasing number of hidden units as you move up, and shown that it reproduces proper physics. But my,
really hard to train.
Yeah. Yeah, actually, we've been trying to train them at phase transitions to address this, and they are surprisingly hard. I wish somebody would have told me. So they, in that paper I cited, there's specific cases where they're successful in training, and people are still working on this. But also, the power of the renormalization group is almost in the sense that you kind of flow to a single or a finite set of very well-defined features when you move up. And I'm still not sure that philosophy between kind of moving towards what I would call this field theory and moving towards maybe a finite set of features is completely transferable. But there's also arguments that images, natural phenomena like languages and stuff, occur near phase transitions if you look at natural images and stuff. And so maybe conversely, that's why you need deep machines or deep learning to classify natural images, is because somehow in some perspective these things look like they're near phase transitions. Yeah. Did you have a question? Or did I answer it?
My question is more about, like you presented in a kind of logical way, the story of how it brings together, but...
Thank you. I thought it was completely random.
Were there some creative insights where you saw some connections between fields we hadn't seen before? Can you talk a bit about the creative process in your group and in your work that...
Sure. So 2 years ago, so we've always worked on algorithms. So that's what we do. We do algorithms, diagonalizations, tensor networks, Monte Carlo. So I thought I knew the algorithmic landscape very clearly for quantum systems. I had a student who graduated from my group, a PhD, And Waterloo has these like job fairs for Silicon Valley, and Intel hired her without even a reference letter from me. Just she gave a talk on quantum physics, bang, moved to Portland. I said, what? You know, what are you doing out there? And she's like, oh, we're doing machine learning. So they're basically characterizing, like I say, classical like chips in the manufacturing process. So they use very advanced machine learning algorithms to classify defects and stuff like that. I think all the manufacturers do this type of thing. So that was interesting, number one. But then I was thinking, like, what skills transferred, you know? And so once I started looking into it, I realized exactly. So really, industry was ahead of us. The industry knew that certain physicists, you know, could do this type of work. And maybe because you guys don't graduate enough PhD students, they were desperate, right? And they go to Waterloo and look for physicists. So then we started thinking about, like, you know, we started researching your algorithms and tried to look, you know, for reasons that they were interesting to us. And then, you know, the whole thing just fell open to us, I think. This field really took off now in the last year. I mean, there's tons of papers that physicists working on traditional, you know, condensed matter, statistical mechanics, who are now repurposing algorithms from industry.
How much do you think that has to do with just widespread literacy in machine learning?
Yes. I mean, yeah.
Deep connection.
Well, so we're not great about literacy in our field. Like, you know, you don't know our algorithms, and so there might be potential for machine learners to work on, say, quantum Monte Carlo, but they've never been exposed to it, so that's part of it. I mean, we have transferable skills both ways. But also, you know, there's tens of thousands of engineers or more working on machine learning algorithms now, and they're making real progress, whereas there's maybe a few dozen physicists or 100 physicists working on our algorithms. So I think potentially your field's moving faster, and so some of this technology can just transfer, you know, into our field just because it's being created, you know, in this big ecosystem that you guys have created. So, yeah, it's not completely clear to me why these things happen, but there's definitely crossovers. Yeah. First, or
Only case where you couldn't do that with 50%.
yeah.
Mm-hmm. If you take a big region, you take the statistics of local patterns, they're the same in those two regions. If you take a smaller region, the fluctuations in those statistics are different.
Yep. So I would say that's what I would call the local constraint. I think that the fact that those 8 plaquettes, in a small region you have to have those 8 plaquettes. I think that's basically what the filters do when I do the CNN. So, yeah, I think that's very important insight. I would also be interested to see is, you know, if I can detect something global. So what I call topological. You have an image and there's a line that goes non-trivially around that image, or if you have a 3D image and there's a hop link, I would call that global. I would be interested also. Pardon? Good.
It's easy to do it if you want to iterate algorithm. So recurrent vectors are quite easy. But you have to have a very deep and widely connected connection to it.
Yeah. So this is great. Yeah. Thanks.
A big question in machine learning is what qualities are tackleable or deep learning. And I was curious with this connection of physics, if you have any intuition about what type of multiplications would be practical or
yeah. So I think this is the central question. So, you know, our algorithms, physically, we built from basically in low dimensions when you have finite entanglement. So when your electrons, you know, you can separate them and they can be non-local. If that entanglement isn't too far, like if it's quasi-local, then we can design algorithms based on that physical input that are efficient. But people suspect that, at least in some cases, like an RBM can solve one of these problems that's not in that class. And so the question is that a reduction of exponential scaling, which would mean that RBMs can solve a different class of Hamiltonian than we're used to, or is it just the prefactor? And then even though it's useful, it would mean that it's like the question of difficulty. I always find that the same Hamiltonians, which one method can work on all the methods in quantum physics. So the idea that there could be some new class of Hamiltonians that could be solved with some sort of deep machine. I think that's what's most exciting for people like me. But we have no idea yet what that class looks like, what the structure of those difficult problems looks like. I don't even know if I answered your question, but I just...
You also reference this work on CS5.
Right.
That's where you went to top side. All this quantum-based networks. The space networks are another way to keep going in space. But they also can be restructured, so you can actually start with something that doesn't have to be randomized like a deep learning network. You can actually put some of the quantum physics already in there, right? And then you start training it.
Right. No, we haven't done that, but I think this is kind of one frontier where you take some physical knowledge, like, we haven't specialized much your technology. Like, we haven't specialized much to these physics applications, this idea of general connectivity and so on. But I believe that if we do a little bit of specialization, maybe along the lines you're thinking, like I haven't done it, but I think there we could see big gains in physics problems. So yeah, I haven't looked into that, but I think it's definitely one direction that the field will take. Yeah.
All right. Well, that's great. Thank Roger for very.
Thank you, guys. Thank you.